back with homework 8, and this is problem 2. And so we have this device here with another ES143 Engineering by Design student project. And we have this collar that has a mass of 6 kilograms, and it's resting on top of this lower spring. It's resting on it, which means it's compressing the spring. It's also, the spring is not connected to it, right? And it's get pulled by this cable right here, by this force of 175 newtons. It's got this massless and frictionless pulley. The dimensions are 300 millimeters this way. 450 is the distance the thing is going to move. So what's going to happen, all right, and then this C is sort of like the distance from the middle of this thing to the top edge right there. So when it's pulled all the way up, it compresses this upper spring 75 millimeters, right? So what they're saying is that the middle of this ends up at this level right there, if that makes sense. I think you can see my cursor, right? And at that moment, we observe that it's traveling at 1 meter per second. So what we need to find is the, I messed up. I need to fix the problem here. Let me fix the problem before I publish it. That's a good idea. And through the magic of pausing, you could see that we're asking for the upper one. So that's K2, that's spring constant, right? So let's see. I've written out the basic problem here, and so what we want to do is maybe I want to sketch the thing in here. Dash 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 dash, and dash 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 dash. I try to pick a problem where we're trying to find something other than the end velocity, right? But it's starting from rest, so we can write out our basic equation, KE1 plus PE1 plus work done to the thing is going to be equal to KE2 plus PE2, right? And so KE1 is going to be equal to 0 because it's starting from rest, nothing's moving, no kinetic energy. PE2, I had to do this over to the side. Before I do this, so I had to do a little preliminary stuff right here. We need to find out how much deformation is in this first spring. So do I have to do a free body diagram for this? I don't think so. I think we can establish that the spring deformation del 1, let me write this out right here. Okay, the weight of A is going to be equal to K, I like to make those lowercase k, sorry. Lowercase k1 times del 1, right? So that would say that del 1 is going to be WA over K1. And WA is going to be mass, that's 6 kilograms times 9.81. So I picked a metric problem as our second one. And that's going to be divided by K1, 600. So that's 6 times 9.81 times, okay, and divided by 600, we get that it's 0.09810. Did I do that correctly? I think I did. Okay. Meters. So if anybody wanted to know, it's 98.10 millimeters. So now we can go to PE1. Oh, and by the way, let's make sure we have this correct. This is going to be state 1, and this is state 2, and this is the datum for gravity. All right, so it's going to start out with no potential energy except for spring potential energy. So we'll have PE1 is going to be 1/2 K1 times del 1 squared. So we have 1/2 times our 600, yeah, times our del 1, which needs to be in meters, 0.09810 squared. Did I do that correctly? I think so. Although I'm a little, where did 600 come from? Oh, it's 500. Why did I do that? I put 600 up here. All right, let me fix that. It should be 500. All right, so I messed this up. So this is wrong. And that's wrong. And that's wrong. So definitely not a scripted show. So 6 times 9.81 times, and then divided by 500, I get 0.1177 meters, which, just for our own edification, we know is that many millimeters. 500, 0.1177. I can close that down a little bit. Look at the whole meter. I think I did that correctly now. We'll square that and multiply it by 500, divided by 2. And I get 3.465. And these are Newton meters. That's the energy, aka a joule. If you call it a joule, they're the same thing. I like the Newton meters because we use the pound feet or the feet pound in the US units, so it just makes it symmetric. Now, the work that's done between 1 and 2, I actually have to do a little bit of geometry here because we have to be careful. It's only the distance that the force travels. Well, how much distance is that going to be? It's going to be this length minus this right here, right? Because this length is going to be closed up, right, as it's getting longer right here. So the amount, the distance this thing gets pulled is this length from here to there minus this distance right there. So I think I'm going to write that as a thing right before I get into writing the thing right here. So I'm going to say, what do I want to? How do I want to call that? Let's just say delta L. I didn't know what else to call it. Is going to be the square root of a squared plus b squared minus a. And I'm going to do it in millimeters just to make my life a little easier. I don't have to write out so many. I guess it doesn't really matter. It doesn't really matter. It's not going to make any difference. It's going to be 0.3 squared plus 0.45 squared minus 0.3. And so we go 0.3 and square ya and 0.45 and square ya and add ya and square root ya, and then take a 0.3 and subtract it. And do I get the same value as before? I did. Yes, I did. Okay. So it's going to be 0.2408, and these are meters. I did turn them into meters. There we go. Okay. And so for the work now, between 1 and 2, that's going to be my force times my delta L. So my force was 175 newtons, and the distance it went was 0.2408 meters. So 175, and I get 42.15 Newton meters, or joules of energy that's been added, right? So here is the initial energy because the spring was compressed. It's being released. It's got energy. And now, maybe I'm going to remind myself to bring a spring to class. Okay. Now we're going to have the kinetic energy at state 2. It's going to be 1/2 mass velocity, I guess the velocity of A. It doesn't really matter. It's just velocity. The only thing that's moving is the one part that's moving. So it's that squared. All right, so it's going to be 1/2. The mass of it is 6 kilograms. And they told us the velocity is 1. Right? So we could actually do that. That's just 3, isn't it? Did I do that in my head right? I think it's 3, yeah. 3 Newton meters. I used 4 sig figs there, even though I didn't need to. Just to try to show you what's the right thing to do. Alright, so the potential energy at 2 is actually going to be 2 parts of it. There's going to be the gravitational potential energy, because it's here. It starts out at 0, but it's moved upwards. So it's moved up b distance. So we're going to say that's going to be mg, and then direct h, right? But it's going to be plus 1/2 k2 del 2 squared, right? But here's what we're trying to find, is that k. So let's start out with this guy first, and that's going to be 6 times 9.81 times the distance that is moved. It's going to move up b, which was 0.45 or 450 millimeters, 0.45, and then plus 1/2 k2 is what we're looking for. So let's leave that as a variable. And then del 2, we were told it has crushed 0.075 squared. Alright, so I'm not 100% sure I did all of this correct, because I ended up with a very large number, but that's okay. Let's see what happens. Alright, so we put all of these things back up into this equation. And so we start out with 0, and then we have the meager 3.465. And then we have what's the main driver of this is this guy, is 42.15. And then we, what we're left over, oh, not plus, equal K2. Oh, I never wrote all the rest of this out. Let me put a pause into this. Let me write what these guys turn out to be. So 6, 9.81. And 0.45, right? So this turns out to be 26.49, right? So that's quite a bit of that getting eaten away. Plus, we're going to 0.075 squared divided by 2. So I'm going to have 2.813 e minus 3 k2. So that's what I'm going to write down here. Plus 26.49 plus 2.813 e minus 3 k2. So k2 should be equal to, let's see, still use that, minus 42.15, I'll subtract it out. I want to subtract out 3 from it, and 3.465 subtracted from it. Okay, now I'm only left, that's not a lot, so I'm going to divide through and take the square root. Okay, see, it's a much smaller number than I had before. A little concerned by that. I think I did everything okay. I'm not 100% sure what I might have done wrong, so I might want to look at it again. But I found I got 57.19 Newton per meter. That's going to be what my K is. I'm going to look through this again, double check my numbers. So I'll do it real quick. 42.15 and 3.465, add them together. I'm going to subtract out 3, subtract out 26.49. Alright, so I have smaller than I had before. I don't know how I did that. 3.465 and 42.15. Add them together. Subtract out 3. Subtract out 26.49. Okay, so I got that again. And I have 2.813 E3 minus divided square root. And now I got a different number. The old number here, I see what I did. I didn't like square root it, but here I got 75.71. And I think that's going to be my answer. I'm sure I have some amount of suspicion that I did something wrong, but here we go. That's going to be good enough for this one, I believe. So I know I went through it pretty quickly. I hope you didn't just watch this video. I hope you actually worked through the problem as much as you possibly could and paused the video at various places and just proceeded and then got an answer and then came back and watched the video, because otherwise you're not going to get as much as you can out of this whole process.